Yeah, good afternoon, everyone. Myself is Dr. H.S. Godana Swami. I'm currently working as a professor and head of civil engineering, ACS College of Engineering, which is at Mysore Road in Bangalore. And it is the part and parcel of the RR group of institutions. Today I'm here with you to discuss some of the important facts connected to the fluid mechanics or the hydraulics concept. Especially this, my conversation or my talk will be, I hope it will be very helpful for the beginners who are just start teaching the fluid mechanics as a teacher in the UG classrooms. And I'm basically a hydraulics person, and I'm sure that I can talk good things about you for a beginner, so for the fluid mechanics or the hydraulics studies concerned. Now let's begin with, I have a teacher with me in front of me sitting and listening my talk in live. I wanted to start my conversation or talk with the definition of the mechanics. We know in engineering we have many applications, and force is a very important member in the system. When I particularly come to the study of mechanics of fluids or the hydraulics, pressure becomes a very, very important factor in process. Like structural engineering system, force and loads, we speak more, but in so far hydraulics or hydraulic machines, fluid mechanics is concerned, we talk about more of the pressure. So I give much importance for our discussion on the pressure because I will be talking on the fluid mechanics is concerned. So let's see what is the mechanics in general. Mechanics is a life science subject. It is, we say it is a mother nature where behavior is to be studied on any object. It may be a solid object, it may be a liquid object, or it may be any translatory object. If I am interested in studying the behavior of such a material completely to understand its properties, both physical and technical properties, I need to have a better understanding of the system first. So mechanics is a very systematic study of the forces, pressures, and its effect on the bodies, whatever you are going to connect it with. So as a hydraulics person, I am connected with the fluid mechanics part. So I restrict my talk to talking about the fluids only. So what is the fluid mechanics then? After understanding what is the mechanics, mechanics is nothing but study of behavioral properties of materials in general. But when I particularly come to the fluid mechanics, I need to understand what is the fluid mechanics then. So fluid mechanics is a study of behavior of fluids. How fluids behave at different instances or at different, when they are under pressure and when they are not under pressure, when fluids are in motion, when fluids are in rest, and when fluids are in translatory motions. And all these complete study we make in the heading called the fluid mechanics. And it is always very important to understand who is the father. In life sciences, father is very important. So like that, every subject of engineering will have some the involvement of scientific inventions is concerned. So Prandtl, P-R-A-N-D-T-L, Prandtl is the father of fluid mechanics. It is believed he is a German scientist, and he born in 1875, and he popularized it. It is believed that among the engineering fraternity, he popularized the subject fluid mechanics. He is basically a fluidician working in an industry in the German in 1875. So coming to the Always a question arises in the engineering minds, why I need to study? Why I need to study strength of materials? Why I need to study the materials of construction? Why I need to study solid mechanics? Similarly, the fluid mechanics also have a question, why I should study the fluid mechanics? What is the benefit that I am going to get by learning the fluid mechanics? Dear friends, I would like to tell you that fluid mechanics has got enormous applications is concerned. So normally we have very variety of applications of fluid mechanics. I just start with from the kitchen itself. You have a pressure cooker where you are cooking a rice or a sambar in a day-to-day life. When a material boils properly, you will get a visual. By that, you will be switching off the pressure cooker system. I'm trying to make a common understanding of this subject. Okay, I'm not much concentrating as a technocrat, but I'm just concentrating on as a lifetime day-to-day user. So your mechanics study will start from the basic, what is called a pressure cooker system, simple cooking of rice and sambar. How do visual makes a sound? It is because of the pressure inside the vessel that creates the noise. By that you get awareness. You have to switch off the cooker system because material inside is properly boiled. So your scientific invention started from day-to-day life. So fluid mechanics is a very enormous, a big application subject where you use starting from a small needle to flying in the rocket or flying astronaut in a satellite system. Such enormous applications the fluid mechanics delivers into the minds of the engineers. I will just discuss some of the important applications so far practical is concerned. So number one, you go to the automobiles. Take an automobiles example. In automobile, we use the liquids like petrol, diesel, where that oils will be burnt. By burning of oil, you get the heat, and the heat is converted to pressure, and by that pressure, vehicle moves. A locomotive action or operation will take place. So fluid mechanics is very important in vehicle industry because the fluids are, when heat, they produce an enormous quantity of pressure which will help the vehicles to move. Now I will just move on to the hydroelectric power plants. All the fluids will develop the potential energy and kinetic energy, you know very well. The fluids can develop the kinetic energy and the potential energy because of their height and motion. And this height and motion is capable of rotating a turbine when they pass through a large penstocks, by which a Pelton turbine, it may be a Kaplan turbine or a Francis turbine, it can be rotated in a desired speed by which electricity is generated. So water is a very important fluid material where you are using an important source in generating an electric power. So fluids are very much used in hydroelectric power plants. I'll move on to the nuclear plants. You know very well nuclear energy is also one of the important supplement energy in nature, apart from the thermal energy and the water power energy. And you need to collide or make a collision of uranium-235 to produce the heat in a nuclear power plant, and a large quantity of heat is going to develop inside the system, and if that heat is not dissipated, there may be a chance that nuclear plants can blast because of the overheating. For that, what is the role of the fluid now? The fluid which you are using to dissipate heat as a coolant. As a coolant, you are using the water in nuclear power plants. So like this, I can go on listing so many examples, so on, unlimited examples for the fluid mechanics concern. And nowadays in the technology industry like aeronautical and aerospace industry have very wide applications so far fluid mechanics concerned, especially the fluid dynamics is concerned. You need to launch a rocket, you need to put up the satellite system into the orbit, and you know very well it has to cross number of the atmosphere layers, and your rocket system should jump from one layer to another layer. It has to exert its own self-pressure by which it can jump to the one orbit to another orbit. You need pressure of the engines. You need the engines to be blasted off from one range to another range. Which is working? It is the fluid dynamics which is working. The fluid dynamics theory, fluid dynamics practical concept is working in making your jet engines to fly off to high altitudes because of the development of high pressures. Dear members, it is because of the fluid dynamics only. So understanding fluid dynamics also help the preparation of the rocket engines, launching of the rockets, and so on. So we have not let out the fluid mechanics application starting from a small needle required for threading in a home to a satellite launching machines. So with this, I hope you understood what is the importance of fluid mechanics, why I need to study the fluid mechanics as an engineer or as a science engineer or as a system engineer. Without understanding properly the system, you might have seen in many accidents occur in launching the vehicles, launching the space shuttle vehicles. It might have burnt in the middle before it reaches orbit. What may be the reason? The reason is the failure of the fluid dynamics, not the construction, not any other thing. It is the failure of understanding properly the fluid dynamics and its process operation may be an important serious reason to fail our launching of any rocket systems. I am just quoting this information based on the source of information obtained from ISRO. And I am the regular reader of that ISRO magazines because basically I am a hydraulics person. I need to understand the hydraulics behind the system. So I just keep on remembering those incidents, how a mission system failed because of lack of understanding of fluid dynamics. What is the major problem that I have seen from in my last 2.5 decades in teaching this subject is, we are only restricting ourselves to a curriculum content in the syllabus, and we are delivering only that part of the syllabus for the students, not making really them to understand practically what happens if you don't understand fluid statics dynamics properly. And you might have also seen some ships are being sunk in the sea. What may be the reason? The reason may be a fluid statics, not understanding properly the Pascal's law, not understanding properly the Archimedes principle, by which the many boats or the big ships might have sunk. Similarly, what is happening in the outer space? Similarly, same thing. So recently, Chandrayaan-1 didn't launch into the moon surface. Probably the engine did not produce enough energy to land it on the moon. Close to 2,700 crore rupees has been spent for the Chandrayaan-1 for launching the missions. But at the stage of 13 seconds, less to land on the moon surface, the jet engine failed to produce the required propulsion. Failing which, it has absconded. Till date, it was not known what happened to that launching vehicle. So that the jet propulsion theory is also based on the fluid dynamics. So, dear friends, so I hope I convinced you the importance of studying the fluid mechanics as an undergraduate and a postgrad engineer, and try to enlighten in your mind the interest in study to fluid mechanics. Yes, some good information is there in understanding the concept. I believe that I have made you to enlighten, to think on those aspects, to study seriously about the fluid mechanics. Now let me just go on to the, once you understand the importance of fluid mechanics, how do I take as a study purpose? Always sampling study is very important in engineering sciences. So I classify the fluids basically into two types. One is the liquid state and the gaseous state. And you know from your basic of theory you already understood the fluid main classification. Scientifically, I can classify the fluids into two groups, and one is in the liquid form, another is in the gaseous form. And every material will have its own advantages and disadvantages also. You look at the compressed natural gases, which you will be using in automobile industry, and liquefied petroleum gases, LPG, which you are using in the home industries. And these are all the examples for gaseous state of fluids. And that have a different chemical, thermal, physical, and engineering properties. As I said in the beginning of this talk, I am concentrating only on the liquid part of the fluid mechanics. So, henceforth, whenever I say fluid, it refers to the liquids. So, in liquids, you have oils, waters, blood, ink. These are all which are capable of flowing and which have a capacity to develop the friction, which have a capacity to develop a surface tension, which have a capacity to develop a surface tension. All we say there as fluids. So an engineering definition, as per you refer any book, the engineering definition normally says, substances capable of flowing and which undergoes continuous deformation, even a small incremental force is applied on it and is called as a fluid. I am just defining a very practical book definition, but you may have a very a long form of definition for that fluid. I am restricting myself only for engineering teaching faculty only. So I just conclude like this. So fluids are the substances which are capable of flowing, and while flowing, 100% they develop viscosity, 100% they will develop friction, and 100% they will develop the surface tension forces. And when I come to the classification of fluids, I said only the scientific bifurcation how fluid is classified, as I said, in gas and liquid form. But liquid again is classified into a lot of categories based on the characterization and the properties. How do we classify chemically, how do we classify biologically, how do we classify engineering-wise? Will make different classification of the liquids also. So whenever I say liquid or fluid, it means refer to the liquid in general. So we have real fluids and we have ideal fluids, we have ideal plastic fluids, we have Newtonian liquids, we have non-Newtonian fluids, and sometimes we have even beyond that also. So all these classification is based on the characterization in the process and also the characterization property that is being exhibited during the demonstration of the experiments. When I come to the, see, for example, an ideal fluid, it may be purely imaginary. For theoretical purpose, fluid may be an ideal, but an ideal fluid is the one where it does not have viscosity. And practically it is proved by the engineers that only super helium do not have a viscosity. But however, when we teach for the students, we say only mercury do not have the viscosity. It has no adhesion and cohesion effect, hence that does not possess any viscosity. Rest all other liquids which exist in the nature will have some viscosity. I will come later what is viscosity, who invented viscosity, what are the different type of viscosity, why I need to understand viscosity of the fluids. I will come on the later part. But as and now, you have very characterized properties so far fluid is concerned. So practically I believe that, I hope many of my friends believe that practically the ideal fluids do not exist in nature. They exist only for the theoretical purpose. All the liquids exist in nature are called as the real fluids. Example, oil, water, ink, blood, plasma, whatever that capable of flowing is treated as the real fluids. Whenever I say real fluids, they possess continuous deformation while in movement, and continuous friction is going to develop, and some sort of surface tension also develop depending upon the situation where I am using the fluids. And you know very well Newton is a very big scientist who invented in all the direction of the science and engineering. In fluid mechanics also he contributed many important laws connected to the fluid mechanics. So according to the Newton's second law of motion, you have a change in force is proportional to the momentum. A net force acting on a system is directly proportional to the momentum. Momentum in common sense we define as a product of mass and velocity. or mass and acceleration. So this concept, the Newton's concept, has led to develop the classify the fluids into Newtonian fluids and non-Newtonian fluids. So it is direct relation between shear stress and the shear strain, because the liquids are always subjected for the shear stress and shear strain. Because you cannot make float the liquids in the space. You have to make the liquid to flow on some surfaces. You are going to create a boundary there. So whenever a boundary theory is involved, a boundary concept is involved, definitely there will be the two objects which are moving related to each other. So they come to existence to the Newton. There will be a shear stress, there will be a shear strain, and those liquids which satisfy the direct relation between the shear stress and shear strain are called as Newtonian fluids. And the fluids which do not obey this law, I mean to say, where shear stress is not directly proportional to the shear strain, we straight away say they are non-Newtonian fluids. For example, the human blood is a non-Newtonian fluid, whereas the water and the oil is a Newtonian fluid, and the blood and the plasma and the printing ink are referred technically as non-Newtonian fluids. And when I come to the ideal plastic fluids or a real plastic fluid, after a certain stage, it may be due to heat or pressure, the liquid may change to another stage where it cannot regain its original shape and size. And that state we call as a plastic state. And you know very well, plastic never it's regained unless it heats up again. So we say sometimes the liquids are the plastic liquids where they cannot regain their shape and volume once the applied force is removed. So my idea is to say that whatever liquids we study in engineering or in science is concerned, they are all the real fluids. Again, I want to remind you, the real fluids always exist in nature, and they will produce a continuous deformation, and they will produce a continuous frictional forces, and they will continue to produce the viscosity forces. The property of viscosity also is very, very important at this stage. At this stage, I just wanted to make a note of a viscosity property. Of course, the viscosity is also found by the Newton only. It is a very simple property where material experiences some frictional resistance. You take an example, a water and an oil with you. Just make an experiment in your home. You pour the water, it will move little speed. You pour the oil, it may not go little speed. What does it mean? What you are trying to understand by this demonstration? This demonstration purely tells the movement of the liquid related to the surface. The liquid is moving fast and oil is not moving fast. What is that is making oil to move slowly? What is making the water to move fastly? Gentlemen, that is where the viscosity comes into the effect. So viscosity is that property of the material where it experiences the resistance to the flow. That resistance may be very small, I don't know. It may be very small, it may be very negligible, or it may be very large in some cases, but there exists a resistance. But due to that resistance, the material movement may be restricted. And that is where the viscosity plays a very, very important role in fluid mechanics. So understanding viscosity is also very, very important in fluid mechanics. Unless I make a complete property understanding of liquid, you cannot put the liquid into a practical use. I cannot make mercury to flow in the pipelines, but I can make the water to flow in the pipelines. I can make the oil to flow in the pipelines. I can make the compressed natural gas to flow in the pipelines. So their viscosity property plays an enormous role in fluid mechanics, and luckily Newton has given a lot of technical innovations, details connected to the viscosity is concerned. Just for mathematical purpose, viscosity in engineering level, we tell to the student there are two types of viscosities. One is dynamic viscosity, another one is the kinematic viscosity. This purely depends upon the phenomena where this liquid is subjected. So if liquid is not in motion, we say it is in a static viscosity, or it may not be a dynamic viscosity. Wherever there is a movement between the two objects in a liquid, we talk about the dynamic viscosities. And wherever forces are not considered so seriously, we bother only about the motion, not bother about the forces. Then we talk about the fluid kinematics or the kinematics of the viscosity. So only motion is important to me, not the force which is creating the motion is not important to me. So according to that, we classify a dynamic viscosity and the kinematic viscosity purely based on the inherent property of the material is concerned. So with this background, I hope I made very clear to you what is a fluid mechanics, what is a mechanics, and why a mechanics needs a study technically, very systematically. What it makes a huge loss in terms of money, material, manpower, if you do not understand, if a technocrat did not understand properly a fluid mechanics. I have just quoted some example, whatever I have gone through in my academic experience. And somehow I made you convincing how fluids are classified, both scientifically and technically. What is the role of Newton's in classifying the fluids and other things. Now I move on to the very, very important aspect of principles of fluid mechanics. Any concept without the principle cannot be accepted technically. I may say very blindly, F is equal to m into A. Action and reaction are equal and opposite. And I personally quote while I am teaching the elements of swimming to all my undergrad students. So, dear students, whenever I say action, reaction, equal and opposite, may not be proved in all the cases. And students look at me very curiously what teacher is saying. Then I do explain them, let me have a steel ball to you, given to you, throw to your opposite wall. Does it return back? No, it will not. I'll give a cricket ball, it may not. I'll give a tennis ball, it will bounce back. So as a teacher, I will make a concept-wise explanation to them. What happens? What is happening? What is happening to steel ball? What is happening to cricket ball? What is happening to a tennis ball? Why they are not rebounding? Do you mean to say that Newton's third law is invalid? No. Every law, every principle has got limitations. Under that scope of study, the laws can be valid. So I need to just bring you to the information. The elastic property of the material plays a very, very important role in making success of Newton's third law. Unless material have a rebounding power, elastic power in it, action and reaction cannot be equal and opposite. Then students will put a smile on their face for understanding the concept. And I always advise to all the young teachers who is teaching fluid mechanics or a hydraulic machines, please make a demonstration of the student. Understand the concept using the devices, using the demonstrative procedure so that they never forget the phenomena of the fluid mechanics. But unfortunately, I am very sorry to say this, many times on the board, we teach only theoretical concepts. We never make them to understand practically. Probably this may lead to a broader scale failure of the systems in general when they grow up, when they join some industry. They may not be undergone rigorous practical study, fail to understand fluid statics, dynamics completely, leads to a lot of failures. I'm just imagining, I don't know. I'm just putting my words very honestly in this. So coming back to the, I'm talking about the principles, very important principles in fluid mechanics. So like I said, the father of fluid mechanics 1875 proposed very three important principles on which a fluid system operates. And that system, which is called number one, is law of conservation of mass, and the law of conservation of momentum, and law of conservation of energy. So being a fluid person, you need to understand all these three principles very, very correctly and neatly. Because these principles are nothing but heart and brains of the fluid mechanics. Law of conservation of energy, mass, momentum, all three are regarded as the hearts of fluid mechanics. So I'm just going to give an example for each. If you go to the law of conservation of mass, a continuity equation, what you derive. I make a discharge of water from point A to point B, believing that whatever that water I put at the point A will surely come out from the point B. If I measure it, I may not have a loss of even single drop. What does it mean? It means that the mass is transferring continuously same from point A to point B. So I mean to say the continuity principle is followed there, which directly relates to the law of conservation of mass. Mass is conserved at every point along that line without losses. Unless I specify very specific losses, the mass never changes. And this is the fundamental basic principle of fluid mechanics, where we understand so many equations, we derive so many equations based on this law of conservation of mass. When I move on to the law of conservation of momentum, probably if you remember when you are teaching applied hydraulics for your first sem students, I believe that you might have taught the impact of jet on vanes or impact of a jet on turbines. So there you try to define what is the momentum. And you have defined the momentum and impulse principle also. That is the basic principle behind rotating a vane or a bucket in a turbine. So law of conservation of momentum helps you to understand what may be the impact of a jet on the vanes or on the buckets which are mounted on the turbines. And you know turbines are the machines which converts hydraulic energy into mechanical energy, and mechanical energy in turn converted into electrical energy. So basic principle behind is the theory of momentum only. Mass is converted into momentum. Momentum is giving a rotary motion, and that rotary motion is converted into electromagnetic force, and this electromagnetic force is nothing but a form of electricity. So the entire principle behind is law of momentum, law of conservation of momentum. Second important principle in fluid mechanics. Now when I talk about the energy, velocity and the height, I just want you to make you remember, consider, imagine in your mind a dam in front of you, a dam is there. On the upstream of the dam, you have the water, stroke of water, and that water can be flown through a pipe with a good velocity, and that height and the velocity produces some energy. So you are trying to relate, even pressure also going to develop with it. So you are trying to relate the pressure and the velocity and the height, which will be nothing but a concept of energy transformation from static to the kinetic. This conversion of energy from static to kinetic will produce a rotary motion for the turbines. And that is nothing but a theory of conversion of energy in the different forms. So law of conservation of energy is third important principle where you need to understand extensively so far the turbines motion is concerned. So based on this law of conservation of energy, we derived another very important equation which we use both in hydraulics and hydraulic machines. Probably I think you have to recall that equation. That equation is called Bernoulli's equation. Bernoulli is once again a Greek scientist who conducted many experiments connected with the height, pressure difference and the velocity. And he related these three parameters, very important parameters in fluid mechanics, and he derived a very popular equation, what is called the Bernoulli's equation. So basically, Bernoulli's equation relates the height, pressure and the velocity, the potential energy, kinetic energy and the datum energy. When you combine all these three types of energy, the energy is converted as a rotary effect, and rotary effect will produce the electricity. So law of conservation of energy is also very important principle in fluid mechanics. So you need to understand, if you want to be a perfect fluid mechanics and expert in understanding the statics and dynamics of the system, you need to understand thoroughly all these three principles. You have to make your students to understand well about the concepts by giving a lot of practical exams, practical examples of the process, not just simply deriving some equations, solving some problem, will not make you to understand these principles. You need to really explain a very well way in understanding law of conservation of mass and its importance, law of conservation of momentum and its importance, and law of conservation of energy and its importance. Please try to deliver your lecture through the model study, through examples, through real-time examples. Obviously, you can make your class of fluid mechanics very wonderful, very interesting, very curious. Because this subject may deliver in the student mind lot of curiosity. You can put it in a mind. At the end of the classes, you put some questions. Let them go to the internet and search, yes, what may be reason for this? This make you definitely lot of curious minds, ignite lot of curious scientific innovations in the mind. Obviously, your class becomes very interesting, and you will also be very interested to teach this subject. And I believe that in my engineering fraternity, always people will fear of teaching fluid mechanics and hydraulic machines. Maybe the domain may be a problem, but I don't understand. The domain may never make a problem. You are an engineer and you are completed with all concepts. A good study of any textbook will make you to understand this subject very simple, where your student can enjoy this subject along with you while teaching this subject in either in engineering or in post-graduation. Now we just move on to the very important laws that are governed in fluid mechanics. Like I said, the principles are next step of the laws in fluid mechanics. There are many laws where the fluid mechanics governs the system, like the Euler's law or Euler's equations, Proud's law, Proud equations. So every law will have its own limitation. As I said, depending upon how fluid is acting, in what respect fluid is you are putting into the action. So the laws and the equations also the changes. So basically, we have the Euler's law and the Proud's law and so on, where we have used these applications in understanding fluid statics and fluid dynamics. Most importantly, there are a variety of dimensions, numbers, which are used in the fluid mechanics study. If you recall again, when you're teaching for your fourth sem applied hydraulics, the very first module what you teach is the dimensional analysis and the model study. And that is very, very important so far engineering structure is concerned. So dimensional analysis and the model study is very, very important component in understanding the dimensions of the fluid parameters and application of the parameters in building a model, and the model is tested in the real sense. That model we may design and we can put it in the use. For example, I am designing a rocket. I cannot build a rocket of 20 meters or 1 kilometer long in practical. So I shorten that rocket size. What is nothing but the dimensioning. So in the dimensioning, I make the object which I am dreaming to prepare in a small scale. That is where dimension analysis come into play. You need to understand dimensions of the quantities, and you need to understand how dimensions of quantities can be merged each other from fundamental to secondary dimensions, which you can relate a process and an equation can be derived, and that equation can be checked whether it can be tested practically or not. Testing and practical will come in the model study. Dimensions will help you to prepare a model, and that model we can make a study, and that model one day becomes a prototype, and prototype will be used in the real practical cases. That is how you have to link these things. So I am just talking about the dimensional numbers, which are very much used in the fluid mechanics concept. So these dimension numbers characterize the properties of the fluid very, very collectively and very, very conjunctively. So you need to understand what is meant by conjunctively and selectively. For example, I take an example of flow in an open channel. You can have the discharge in open channel in a number of ways. I don't want to go for a detailed study of this classification of fluid flow in the channels. Probably I will talk this content in some other class. But now I restrict only, we have some flow in the open channel. At this junction, I say there may be a uniform flow, there may be a non-uniform flow. Very simple I want to say, I take only a depth as a parameter. If the depth remains constant, we say it's a uniform flow. And if depth do not remains constant, we say it is a non-uniform flow. Just only for common understanding I am speaking. So dimensional numbers will play a very important role in classifying the fluid motions. Whether we have a steady motion, we have unsteady motion, whether we have a one-dimensional motion, we have a two-dimensional motion, we have a three-dimensional motion, whether we have a critical motion or a subcritical motion. Like this, a fluid can have a different variety of motions in the fluid mechanics. And all these studies can be understood by understanding the dimensional numbers. And popularly in fluid mechanics, we use only three important dimension numbers. One is the Reynolds dimension number, and the Euler's number, and the Mach number. So the Euler's number is very much used in the law of continuity equations, law of conservation of mass, and when you come to the Mach number, which will be very, very useful in shipbuilding, in buoyancy and flotation, and metacentric height, metacentric, buoyant force understanding, Archimedes principle understanding, they will require a Mach number. Okay, and when you come to the Froude dimensions number, and all of you have seen a gate system provided in a dam. The moment we lift a gate, the water passes with so rush that they may create another wonder of the fluid mechanics study, what is called a hydraulic jump. Probably you might have seen a hydraulic jump practically. Whenever dam is full, the gate is open, you may see the water is rushing out of the gate and is dashing the water to the mother river. While dashing to the mother river, in between that, we can see a beautiful view of water, a curvature water, and that is we talk about as a hydraulic jump. And a jump is the one which varies the depth of water abruptly. But technically we say a different meaning. Subcritical flow to a supercritical flow will create a hydraulic jump. And that beautiful jump you can say whenever dam is full, you are just standing in front of a dam. Gate is open, you see, experience that hydraulic jump. So understanding hydraulic jump will help you through what is called the Froude's dimensionless numbers. So basically, these dimensionless numbers will relate what is practically happening with the fluid phenomenon. Otherwise, we cannot understand. So when I lift the gate, the water passes and shows some curvature. It is nothing but a practical phenomenon happening. So it is much very well explained by these dimensionless numbers, which are mostly used in the fluid mechanics. In almost all the contents of the fluid mechanics, these dimensions, especially in advanced fluid mechanics, we study the role of dimensional numbers is more of important. So at this part of, I would like to say you have more three important dimensional numbers. So Euler number and Froude number and the Mach number will play a very great role in understanding the practical fluid mechanics, suppose if I want to say. Okay, so once you understand the principles of fluid mechanics, once you understand what is the role of dimensionless numbers and how these dimensional numbers play a very good role in understanding the dimension analysis, and this dimension analysis help you to prepare a model, and this model is tested in various conditions so that a prototype can be developed and the proto can be tested in the real sense. Gentlemen, in all these phenomena, the only concept that is involved is the fluid mechanics. So I hope that I made you convincing that why fluid mechanics is so important in the nature study. It not only helps the nature study, in day-to-day life also it will help you, and it will make a proper technocrat or a techno-engineer unless a proper study of fluid mechanics. So please teach this subject to your students very effectively, making demonstrative experiment, making demonstrative examples, giving lifetime examples will make your subject really fruitful and very worthful in teaching this subject. Probably in next course of time, I will talk about more properties of fluid. Why I need to understand the properties of fluids. I forgotten to mention there are four important properties of the fluid is concerned. So like density, the volume change, and the physical property change, capillarity. These are the just phenomenal properties, but they are not of much of importance so far behavior is concerned. I'll just take an example of capillarity. What does it mean, a capillarity? Probably you may demonstrate this also in the class when you are teaching a fluid mechanics subject. You take a small beer with you and you collect some water in that, you put a small vertical tube in that, the fluid will start rising. Please put questions to the student, why liquid is moving in the upward direction in the tube? What making a liquid to move up in the tube? And if at all it moves, to what it heights? To what height it moves? Why water will not spill out of the tube when you dip this small glass tube in the water? Just create curiosity in the minds of the students. Definitely they will go in the net and search, yes, what is making? Why what is stopped at some height? What is making? So these type of thoughts you have to induce to the students so that the experimental way of teaching the fluid mechanics will help you to understand, make you to understand, not only for the student, probably for you also who would like to teach this subject at advanced level out of the domain. I am just speaking out of the domain. If you are not of the domain, probably you may have some difficulty in teaching this subject. Because understanding practicality, being a domain person is not so easy for a non-domain person. But anyway, I wish you all the best for you to teach this subject very effectively, very demonstratively. In my next course of the teaching, I'll just talk about how properties is to be analyzed, why properties of fluids are very important in understanding the behavior of the fluids. Thank you very much for listening to me. We'll meet in the next course of this.